testing gravity at ever shorter scales by Giorgio.
Okay, thank you. So actually this, I expected this to be an interesting workshop, but as you see, my second half is about Nussbauer spectroscopy. And so I learned about lots of interesting stuff having to do with very low energy Nussbauer transitions, which I was not expecting to learn. So it's been even more interesting than expected, and so thanks for organizing. All right, so what I'm going to do actually is to spend some time, first of all, spend one slide on motivation, because I'm not a theorist and I don't have time to cover everything. I mean, Masha and others can tell you those things much better. And then tell you a little bit about the physics of optically levitated dielectric microspheres and how this is used to try measuring or searching for new interactions at the micron scale. And then I'll describe a new technique using Nussbauer spectroscopy to go beyond the micro scale. And of course, those things, both of them, of course, particularly the Nussbauer one, it's brand new. And so, John earlier told us about third generation ACME. This is first generation, each one and so on. So don't expect too much. But certainly there's actually plenty of interesting progress on both fronts. All right, so first of all, this is the motivational thing. Gravity doesn't fit well with the standard model of particle physics. But maybe the best way to say this is that we generally assume nonchalantly that essentially the inverse square law applies all the way down to the Planck scale, which is this mind-boggling number here. And of course, this is a little bit ambitious, to expect that there's nothing happens, nothing strange happens in that regime. So generally, if you ask how well do we know this empirically, the inverse square law empirically, one expresses, this is not the only way to do it. Maybe it's not the most general, but it's a sort of recognized way of describing anomalies, and that is to essentially introduce a Yukawa term, that is this thing here, which has two free parameters. One is the strength of this correction term, and the other one is lambda, the scale at which it kicks in. And that's actually, I really like this plot, which is modified multiple times from some paper of Eric Adelberger and Ann Nelson and et al. And it's got lambda on one axis and alpha, the strength of the interaction or the absolute value of it, on the vertical scale. And so at different distance scales, it actually tells you how much we know, that is down to what level we know, alpha is less than whatever this black line sort of signals. And you see that I conveniently added to the scale in meters, a scale in astronomical units, because it's actually convenient to actually try to go far away. I can spend 15 minutes describing this thing, which I cannot do, but in different regimes, of course, there's different ways of doing the measurement. And by far the most sensitive happens when you have a periodic motion that actually repeats many, many times, and where there's really no corrections, because at large distance, gravity is essentially the only interaction left. You may wonder how we know that planets are neutral, and to what extent they are neutral, and the answer is that space is conductive. That sounds counterintuitive, but as soon as you have a tiny charge imbalance in vacuum, there's always some electron that decides to fly there and eventually neutralize whatever was charged. So that's what happens here. Then you have artificial satellites here. You run out of steam, by the way, at the boundary of the solar system, or actually quite a bit before then, for various reasons. There's nothing else to do the measurement, essentially, but you run out of steam earlier because of some accidental things having to do with how the orbits are done or happen to be. Then there is a really rough spot here. And this is, if you remember, like 30 years ago or 40 years ago, there was some sort of fifth fork craze. And that was coming in part from this regime here, where essentially finding a fifth force is degenerate with finding oil or water on the ground. And so that's the problem, is that the Earth is not homogeneous on the 100-meter scale or kilometer scale. So it's very hard to do measurements here. And then, this is a meter is somewhere here. Well, a meter is here. And this, you go down to 10 centimeters or something, where Cavendish experiments are typically done. And then you run out of steam on this side, which is actually what the topic of today's talk or this talk. And I don't want to even go through, again, this is a little bit more sort of motivational thing, but I think to me it's good enough to say, look, gravity is such an important thing. I'm an experimentalist, I want to test it better, even without theoretical prejudice, although again, theorists will tell you that this is not just a shot in the dark to some extent. Okay, experimentally, there are two major challenges. One is that as the distance becomes smaller and smaller, the test masses have to become smaller at the same time, more or less. And that means that their volume goes down with the volume and their mass goes down with the third power of the distance, essentially. Okay, so the force is now, m1, m2, and then over r squared. So you gain with the square of the distance, but then you lose with the sixth power of the distance. And of course, the best you can do is to make those things out of platinum, which density 20 or something. And if we could put little tiny neutron stars in there, we would gain many orders of magnitude, but we cannot do that. And so that's actually where we are now. You can quibble that maybe you really want to measure accelerations, in which case you actually lose up here numerator r to the third. And so in that case, still with distance, you lose linearly. But if you measure a force, you actually lose the fourth power of the distance. Now, the more important issue, though, is that when you go below, say, a tenth of a millimeter, electromagnetic interactions are always there to get you. And that is even for neutral micro. I mean, we'll be talking about microspheres, which are wonderful because you can neutralize them and they stay neutral. So that's much, in some senses, much better than having like a cantilever or a torsion balance, which is connected mechanically to the world. Those are in vacuum, they're just sitting there, nothing happens to them. And yet they have, they're polarizable, and they have dipole moments. And so they couple to gradients of the electric field. And of course, you're not stupid, you don't produce gradients of electric field, but there's always a little bit of a gradient of anything or everything. And so that's what actually the problem is. So there's backgrounds. Huh?
So this is almost like a qual question, so I apologize, but like the Coulomb force scales the same way.
Yes.
And as you pointed out, you made this argument about space and that electrons move around. So what is it that actually sets the length scale where this becomes a problem? Like, why isn't it a problem for Cavendish, but it is below this length scale?
I think it's no. I mean, that essentially as you go, that the dipole interaction scales to the cube of the distance. So at some point they cross over. Now, why they cross over around, I claim around the micron, that is an empirical observation. Maybe there is a fundamental reason, I'm not sure. But there is a crossover because one is quadratic, the other one is cubic, essentially. All right. So okay, so that's actually traditionally people have used for 300 years torsion balances, which have been perfected to amazing level, particularly in the last 20 years by the Washington group. And then there's been a little sort of moment of activity, as it turns out, at Stanford, using essentially microcantilevers to do the measurement. But generally, particularly the torsion balance, which is still one of the dominant tools, is kind of some sort of bulky object. And so the hope is that when you're going to such short distances, it's good that everything sort of scales together with distance. And so that's where we are now. In addition, so the way it works, what the idea is to actually essentially put a microsphere, the electric microsphere, which is few microns in diameter, in an optical tweezer system in vacuum, which is shown here. And so now this is entirely is only confined by the light field in here. And so that's also the spring constant is provided by the optics, and the readout is provided by the optics, and it's entirely sort of optomechanical. And then you have to make a trap such that you can go very close, a few micron close, with what I call the attractor, which is some sort of patterned device, that alternates low density with high density, with essentially with a spatial scale, which is comparable to lambda, to the scale at which you're doing the measurement, so that you get a good signal, a gravitational signal by scanning this. Now, of course, you can test for things which are not gravity, so you can, for instance, set contrast of baryon number or contrast of some other property of matter that you want to test, and then you just do a measurement there. But generally, those things are similar, and okay. So our devices that you'll see are silicon and gold, and that's where the contrast is, and then you have optics to produce very carefully the trapping beam. So compared to AMO, we have no idea anything about frequencies. We don't care about wavelengths, or well, actually we care to some extent, but not so much. On the other hand, we are very careful about ray optics because we want to have no halos, or as close as possible to no halos, because as you see, those are problematic when you try to come very close with something that moves. That's tricky. Okay, then the trap is essentially a little device that is, okay, so you can see here, there is a parabolic mirror that takes the collimated light coming in, focuses in the middle of the trap, and then there's the conjugate mirror that makes it collimated again and extracted where the readout is. Actually, the readout by now is way more complicated than this. I realize this is kind of an obsolete photograph. The trapping region is surrounded by 6 faces, or in fact 6 pyramids that go in and essentially mask the beam as it goes in and comes out, but also provide access on the horizontal plane for the attractor, that is this device mounted on a piezoelectric stage, a shield that I'll describe later that comes in from 90 degrees apart, and various other auxiliary sort of devices. Actually, there's metrology, there's some microscopes looking in, and so on. This thing works well, at least qualitatively. And for instance, you can test it by deliberately putting one electron charge or a few electron charge on a microsphere, and then biasing electrically the cantilever that would provide gravity. And when you do that, and in this case, you're not moving anything, or you're scanning slowly, and you see that you're measuring the vector field in 3 dimensions, the 3 components of the vector field in space, and you're checking that indeed everything, this and points down to where you expect it. And can't see it here, but actually there is also, or it's hard to see, but there are both red and black lines. The black lines or arrows are data, and the red ones are an FEA for the appropriate electrostatic configuration. And you see that there is actually very good agreement. And of course, you need to actually make more than one of those views, because this is, because this is a vector field described in 3 spatial dimensions. So there's lots of information here. You can also, this is important, I started saying that once you neutralize the microsphere, which I'll describe in a minute, there is an electric dipole moment left. And you can actually, first of all, that's annoying, because you'd like, if there is a gradient again, that will interact with it. But you can take advantage of it and actually essentially grab the microsphere, but that dipole moment, and speed it up. And you can do it because your trapping region is surrounded by those 6 electrodes, and you can use those. Those are shielding, but also they can be biased to provide this rotating field. The microsphere is also for accidental, who knows why, but it's slightly birefringent. So that's very convenient, because if you provide a linearly polarized trapping beam, you can pick off the small amount of wrong polarization, and then use that, and look at the rotation from the flashing of that thing at twice the frequency. And you can use, by now, we've actually used this to measure the vacuum. You can actually spin up the microsphere, let it, leave it spinning, and look at the relaxation time, do all sorts of interesting measurements having to do with vacuum technology. And actually, those are very small and good gyroscopes, actually, that can be used for other things, but for navigation. But however, what we really care about here is that that's a way to stabilize the microsphere and to average the electric dipole moment from the point of view of the low frequency measurement of the trap, of the gravity. The gravities we'll see scans at a few hertz, mainly because of the inertia of the stage that does this kind. So I mentioned, yeah.
How spherical are they? I mean, they're not.
They're about 1% aspherical. So of course, I don't know any given, microspheres. So actually, my ex-postdoc, Akio Kawasaki, who's at NIST, the Japanese NIST, after now he's doing Ytterbium there. He says, atoms are so much easier. They're all the same. So those things are not all exactly the same. There's some rebellious microspheres that don't work. Some work beautifully. We have one that's been like 3 weeks. We're taking all this beautiful data now that I'll tell you in a minute about, and that's because we have this magic sphere that works really well. But we've taken a lump of those things and put them in an electron microscope, and if you actually fit circles to those things for that ensemble, whatever that is, they're all within 1% from being spherical. Okay.
But you must have to average over the non-spherical nature of them somehow.
There is also some that are defective, and you can see them in the microscope that they're like half sphere, and those you can't even trap. We suspect that those are the ones that just fall off.
But 1% is not a problem?
Okay, let's go. I mean, the answer is that I don't know. I mean, there's clearly their background, there are background forces and so on, and some of those are probably microsphere wobbling a little bit and so on. We're trying to improve this. Sorry, where I am. Okay, so so the first thing is that of course you need to discharge those things, and you do it by the usual way, that is you flash a UV light in the neighborhood, and it turns out that with some practice, and you have to ask my students, I don't know how to do this, but you can essentially go both ways. You start when you load the microsphere, there's 100 charges on it or thereabout. And then you start flashing the thing, and because of this conductivity issue I mentioned, they start becoming close to neutral. Then eventually you get here, and you see now there's 2 charges, 1 charge, 0. And then if you keep flashing, or you flash in a slightly different way, then you cross over and you start charging the other way around. Then, generally you can go back and forth between the 2 charge states by a few charges. Now notice that the signal to noise ratio, this is a Millikan experiment, but with fantastic resolution. In fact, once you're neutral, you are free to boost the electric field that you're using to read out the charge that you have to place. You apply an AC field, and from the motion you actually measure the charge. And so you can boost the field up and actually go for a measurement of how neutral your microsphere is. And in the published data, that is this paper here for us, now 10 years ago, and then more recently, Dave Moore and company at Yale, you actually have sensitivities of the order of 10 to the minus 5 of an electron. You process much less material than the oil drop experiments that were used to actually look for the search for free quarks. So we're much better at looking at very small charges, much worse at looking at small cross sections. Okay? So we're sort of complementary to that. By now, we think actually we can do few orders of magnitude better. In fact, we are starting taking data with one of the 2 traps exactly for this. And we also think that maybe the wisest way of interpreting the data is in terms of neutrality of matter. That is, you use actually slightly larger microspheres, and since you have lots of protons and electrons, you check how well the electron-proton charges match each other. Okay. Anyway, this hopefully there's going to be results soon, but let's actually move on. So dipoles. It turns out that if you have, of course, a dipole in the gradient, it will also experience a force. This is my monopole interaction if I have a charge, which I don't have for the real measurement. And this is the dipole. And then there is an induced dipole term that we actually haven't really studied much. But this term here, we've actually discovered a trick to actually separate it out from this. And that consists in essentially deliberately producing a gradient and then reversing the gradient. And you see, when you reverse the gradient and the field, if you look, your dipole will want to go this way, and also with the reverse case will also want to go this way. But the monopole will actually change direction. And so what you can do is, so you're measuring 2 forces. You're measuring the force on the microsphere with the field in one direction and the force with the field in the other direction. You call those things F plus and F minus. there is a little spatial, how to say, geometrical correction because the trap is not exactly symmetric, but you can calculate that as with an FEA, and that's some sort of a correction. And so you get beautiful results. This is blue and red. I don't remember which one is which, are F plus and F minus, and you see that over time they jump around quite a bit. Those are all calibrated in attonewtons. And now you take the difference, or you take this difference here, and the thing comes down greatly, and it becomes essentially noise-dominated, the result to get. You can look at it in a different way by essentially plotting F plus against F minus, and the permanent dipole moment now is going to go on one axis, and you can see this cloud is very skinny this way. And on the other hand, the monopole axis is this one, and if you project on this axis, you get a very narrow distribution. On the other hand, the permanent dipole moment axis is this other thing here, and you get and the thing is in this case is very broad, and not only that, but also the central value is slightly offset, which is what we saw before. All right, so we can actually investigate that. But now let's actually look at the first run, which is now, I don't know, 3-4 years ago, and no, 3 years ago. And so that's actually the attractor I told you about. There is a shield that doesn't move during the measurement because otherwise there's too much. You always have some patch potentials, and from the surface of this thing, even if it's all nicely coated with gold. Inside there are fingers, which, as I said, are alternating gold and silicon. There's some parameters of this here. You scan this thing at 3 Hertz, and then you look at a bunch of harmonics of the motion. The attractor looks like this, is a cantilever, which is 10 micron thick, made out of silicon, and the pitch or the size of the fingers, gold or silicon, is 25 microns. And then in modern cantilevers, actually we chop this off with an ion beam, with ion milling. The attractor, the shield is some sort of pocketed device like this. Schematically is like this. There is a slot where the beam goes through and the attractor hides behind it. In reality, is actually symmetric like this, just for pure fabrication reasons. But okay, and so that's actually what the data looks like. So the good news is that the noise level. So black is data. This is about 24 hours of data. Black is data when there's nothing moves. Red is data when the attractor is scanning back and forth. And so you see that noise doesn't change much, but you get harmonic, you get discrete frequencies. So this is a background of some sort. Blue is what you expect for a certain amplitude of the Yukawa term, what you expect for a monopole force. And you can see that those two don't match, but yet there is some background. It's not background free. So then you actually, that will limit your reach. And so that's actually the reach. So the bluish thing is limits from previous measurements done with torsion balances. And we were here, which is a couple of orders of magnitude from actually getting into the interesting regime. All right, so in the meantime, we have fixed electrostatic backgrounds, or at least improved greatly electrostatic backgrounds. And then we've discovered that we have an optical background due to the fact that the scanning, even if you do all your optics as well as you can, there is always a little bit of scatter light somewhere in this in the trap. And so as the attractor scans, you get some sort of flicker of the light, and the readout system is not smart enough to actually tell that apart from real motion of the microsphere. So there's actually a number of things having to do with data analysis that I hope can be done. But in the meantime, we have also tried to actually resolve this, from the source, improving the optics, but also coating everything black as much as possible. Now, it turns out that macroscopic things can be sprayed with aqueduct, and old timers may know what this is. But this is very hard to do with this 10 micron thick, kind of thin and thick, whatever thing. And so actually we've learned to actually deposit platinum black, which is what happens when you electroplate platinum, and you don't know what you're doing, but in a very specific way. So you grow this kind of fractal surface, which is very absorbent. And sure enough, you can see that this is a blank attractor with gold surface. And you can see that as function of the wavelength, that's actually how much reflection there is. And this is the platinum black thing, which is 2 orders of magnitude less reflective. So that's actually successful. And sure enough, this is the new data that we're taking now, where you see, this is the data from that paper I showed you before, with the various fundamental and the various harmonics here. And this is the new data that has got at least an order of magnitude better noise and at least 2 orders of magnitude better background. And so I don't know what this results into in terms of alpha lambda plot, because because we're still taking data and we're still looking at how data looks like. So now in the remainder of the talk, I'm going to tell you a little bit about what you do when you're really worried that the electrostatic interactions will sort of get in the way. And this is actually the idea of this came around during the pandemic, actually, by talking to Surjit Rajendra and David Kaplan at Hopkins. And so the idea is that nuclei are much better probes because they were shielded. The electron cloud shielded well. In addition, they have much smaller dipole and multiple moments. And anyway, since they are unpolarized, everything, even the residual interaction scales to the square root of n, where square root of n is how many nuclei you're looking at. So the idea, is maybe we can use some sort of gamma ray spectroscopy to interpret, to actually explore this, which is actually quite satisfying because, my group has been doing particle physics and then nuclear physics. And then I worked on things with lasers and so on. And so this is halfway in between. So it sort of splices the two activities together. But also there is some general thing that I think bugs me. I mean, this has been shown. Actually, somebody had a better plot, better drawing of this, which comes from some sort of scan of physical reviews of many years ago. And so this was the Pound and Rebke experiment done across the street here, where Nussbauer spectroscopy was used to actually do a fundamental physics measurement. Disappointingly or disconcertingly, since then, chemists have entirely appropriated this thing, and physicists don't seem to care about this anymore. Okay, except for inferred yesterday that maybe it's turning around, and so actually it's kind of fun to see whether we can really use Nussbauer spectroscopy for the topic I just mentioned. Just to give you an idea, and again, I didn't realize that there were going to be clock talks, nuclear clock talks. So maybe this is kind of clear, obvious already, but these are some interesting isotopes. This is the data I'll show you, or the work I'll show you is done mostly with iron 57, which has a half-life, the state you care about 100 nanoseconds, an energy of 14 keV, and a relative line width of 6 × 10⁻13. There's a bunch of cases here, which have all been studied and observed, which go down to 10⁻16. Zinc is really annoying because the half-life of the father or mother isotope, parent isotope, whatever, is very short, and so and the energy of the transition is large, which means the experiment has to be cryogenic, and it's kind of this is annoying. But it's down 10⁻16. And then there's those guys. Those are the monsters. Those have never been observed. And they go down to 7 × 10⁻25 for this osmium isotope. This thing has a half-life of 5 hours or 6 hours. Okay, so this is an amazing. These are amazing things. Okay, and so I'll be spending most of the rest on that. So how do you do the experiment? How do you measure a force using nuclei? Well, you don't. You actually measure a perturbation of the nuclear potential due to the external potential. And so the idea, and you can only do this because you look at this perturbation using Nussbauer spectroscopy that has these ultra sharp lines. And so now you have the typical undergraduate experiment where you have a source, and then you put an absorber, and then you have a detector. The detector is just a trivial, well, it's actually a fancy detector because it has to go to a very high rate in the experiment, but otherwise it doesn't have anything special. But the special thing is in here. What you have in here is essentially the resonant absorber, and then next to it you park the attractor, as I call it, which is the thing that perturbs the nuclear potential. And then you scan, either the source or those two things. Since those two things are complicated enough, we scan the source. In this early thing, I had the scanning on the absorber, but that's the same. And so now, as typical in those things, the detector will see an absorption spectrum, so we'll see a line that is sort of a negative line. Okay, let me skip this. So the first thing is that, okay, but I need to go closer than a micron. Is that crazy? Well, you can actually do it by depositing layers and not having really two plates and depositing sandwiches of layers on a single plate. But you can also try to do it really with two discrete plates and get them closer. So you need substrates which are transparent to this 14 kV X-ray energy. Beryllium is actually ideal for this. Beryllium can also be polished very well. And so those are 1.25-inch diameter discs, which are flat within about plus minus 50 nanometers. So yeah, those are flat enough that you can bring them together. How do you bring them together? Well, carefully. You use piezoelectric actuators, which are also calibrated with strain gauge, so that you know how far you move them. And then you measure the capacitance between the discs. That's actually, this is kind of trivial, but I'm very fond of this for some reason. It turns out you can do this with a single capacitance measurement. You can read out 3 degrees of freedom. First of all, when you're so close, there's no fringing. I mean, the fringing correction is time, so it doesn't really matter. So the parallel plate capacitor just works fine. And second, if you do the measurement with time, the same data stream, you can actually tilt the disks in 1 degree of freedom, and you find that the capacitance has a maximum, a minimum when the two are parallel in the degrees of freedom. Then you do it again, you iterate between the two cases. And so with a single capacitance measurement, you can actually parallelize those things and then measure the capacity, measure the distance. If you don't believe the absolute capacitance as measured the distance, it turns out that as you do this kind of tilting kind of thing, the second derivative of this parabolic minimum is an independent measurement of the distance, actually, that doesn't depend on the absolute capacitance. So there is even the redundancy built in. So this is great. This is the calculation. This is real data. But you see, we stop, 2.6 micron doesn't work very well. There isn't a nice minimum. And anyway, that's the best I can show you. And the reason is that we've made a discovery having to do with beryllium. Polishing beryllium surfaces, you may say, well, you poison yourself. No, somebody else does it. But polishing beryllium surfaces results in little grains of the polishing compound stuck in the surface and jutting out on the surface. And apparently people doing this knew, and they didn't tell us because we didn't ask them. So when you make optical surface, the James Webb Telescope has beryllium mirrors. But on a large surface, if you have a few of those things, no one cares. And in fact, when I told to people at Goddard about this, they said, "Oh yeah, we did see some anomalies on the surface, but they were small, doesn't matter." So anyway, so that's actually, so now we've learned this. So essentially, what happens is you start touching with one of those grains, and then your measurement doesn't work anymore. So actually, it turns out that Corning has a process with boron carbide, which is almost as good in terms of transparency to X-rays. And so we're playing with this now, and we'll see whether that works or not. Okay, so the reason I added this slide is that shows one of those resonances with our spectrometer. So we, unlike chemists who want to measure the structure, all the peaks and so on, the only thing we care is whether the peak has moved as we bring the attractor close or move it farther away. So we only measure the line as actually the two most sensitive points on the sidebands. For technical reason, we actually make 4 measurements in 2 pairs because it works slightly better, but that's kind of irrelevant. But this plot is here because in demonstrating our 2 velocity spectrometer that we build ourselves, it only has 2 velocities. It actually compares the civilized nanoelectron volts here with the infamous millimeters per second that somebody complained about yesterday. So this is the truth table for that kind of thing. Okay, so I should skip this and show you that actually we've started running with 5 millicurie sources of iron. This is the blue, look at the blue thing. If you are curious about this, ask me later. And you see that actually, as you take data, there's about 100 days of data here. For the time being, there's no attractor, it's just this spectrometer by itself. And you see that the accuracy at which you're measuring the position of the peak keeps going down with the square root of n, like the dashed line, exceeds Pound and Repka, that is somewhere here. By now we're an order of magnitude and a half below them. We need to reach down 10 to the minus 15 electron volts, which is about 10 to minus 19 on this scale, this E over delta E over E. So we are a couple of orders of magnitude away, which means that in terms of statistics, 10 to the 10,000 times too little statistics. And that's because we want to take data a little bit longer, but more important, we need a much hotter source, which is actually trouble, not because of health physics, but because we're stupid. We can't, out in the Western world, stupid. Ask me later about this. Okay, so there is actually analysis of systematics, and I'll tell you that the dominant thing is second order Doppler effect. This is the fact that Doppler, thermal motion of the nuclei essentially produce a time dilation and a line shift. And this means that if you run a room temperature, I need 30 microkelvin stability, not absolute anything, but stability between the temperature of the source and the temperature of the absorber. Okay, we actually think we have a test where we've reached 100 microkelvin and maybe somewhat better. So this is within reach. I mean, it's not easy, but it doesn't sound impossible. And so eventually, if it all works, with the IRO 57, which is what we're doing now, we use this, and it's kind of annoying that now I just realized that this label covers the thing. But now this is a very aggressive log scale. So those are 3 orders of magnitude. So the part of phase space you're actually covering is quite substantial. Okay, in the meantime, we're also learning lots of things about essentially quantum optics in the KEV regime using Nussbauer spectroscopy. So I'm just hoping that eventually there's going to be something maybe even more interesting that actually comes out. And of course, the connection with the thorium transition are not lost, although somewhat unexplored for the time being. And this is just my conclusion slide that is stolen from Ted Hench. And so John was talking about colliders and so on. I guess these are the colliders in this language. And we are, I don't know if you're, but okay, and that's the cast of characters that are doing this. Thank you.
And the question is, yes.
Sorry, I think I missed it's really cool. I missed just the basic point about how you do this measurement again. So you have a thing, you're measuring loss power, events in it. Why do I change the nuclear potential by bringing something close? Is that the idea?
Yeah, sorry. Yeah, so actually, let's see. I thought I had actually something. Right, okay, good. So because what happens, okay, so let's see there. Okay. Well, because the nuclear, the interaction, the nuclear potential, think about the nuclear potential as a sort of potential well, which is produced by the strong force and all the stuff we don't know how to calculate very well. And so now you actually, if you have an attractive force from the outside, you're essentially opening up that well some, and that will change the level structure there. Now, that's actually why I was bringing this slide up. This is a little bit like neutrino stone beta decay, which is my other activity. And that is, there is lots of nuclear physics between an effect you would measure and calculating what it really means. Okay? However, if I find that the same as in double beta, neutrino double beta decay, if I find that that line shape moves as I bring mass close, well, that's sort of, I'm sure, I am convinced myself and the rest of the world that the systematics are not moving, there are no systematics. That's a big discovery. Now, exactly how that goes into calculating a new interaction strength and so on, I don't know. Okay, and so, which also means that this thing here, okay, so how you obtain this, this thing is somewhat arbitrary and asks Suji. Okay, I mean, this is somewhat controversial, exactly what the reach of these things and so on. I don't think it's well digested enough. I certainly don't understand enough to defend it.
So just as like to get my head around the order of magnitude, I mean, is this an effect that's stronger than gravity?
Oh, yeah. Well, you can see it here, right?
I forget how you measure it.
No, I mean, okay, well, no, this is
This is
10 to the 13 times gravity.
Yeah.
I mean, but you're down, sorry, this is 100 nanometers, this is 10 nanometers, right? And so this is the sweet spot for this measurement, you can see, is in this 100 nanometer to 10 nanometer. Larger distances, other techniques work better, including microspheres. Smaller distances you can't reach, and actually neutron scattering is probably the only way to go at it, or atomic effects. But then, of course, like yesterday somebody was talking about it. So,
Good question.
Very good question. So you mentioned this Gratta, and I think they showed that you could do that much better precision with this other distance. Is that right? And I'm just wondering, like, can you learn something more than what you learned from Gratta?
so
Like,
yeah, so when we started doing that, there were a few milliseconds when we thought we could actually do some Casimir force